I looked at the questions. There are no questions. So let's see. Yeah. Anybody wants to ask? So what are we talking about? Why? Any questions from, let's say, the TS, right? From the forums and so on. All right. Let me try to start up. Oh, YouTube link. Okay. Thank you. Thank you, Balaji. Yeah. Let me follow that.
You can hide your video on the screen, sir. Yeah. You can hide your video. It's duplicating.
Sorry, I can hide my. So this is from the tablet. Okay. We'll do that.
Thank you.
Yeah, thank you. Well, exit full screen. I think. Okay, there are no audience on. Oh, I see. Hello. Okay. So, Vinod, any questions? Okay, one of the questions that I think came up in our discussions was how do we treat gases, right? What is the optical absorption spectrum for a gas? So we understand from actually 11th standard physics that if you have a gaseous element, let's say sodium gas, right? If you look at if you excite it using some sort of a arc lamp, it will emit characteristic frequencies or wavelengths. And we call them as Lyman, Balmer series, and so on. So every gas has its characteristic lines, which you'll see in the spectrum. Maybe there's a doublet, I think, for sodium at 579 nanometers and so on. So if you want to talk about the refractive index of the gases, how will it look like? Any thoughts, ideas?
So gases will have like sharp absorption peaks.
Gases will have sharp absorption peaks. And why is that? Why should it be sharp?
So because there are no, because of the low carrier density in gases, not really have effectively bands or anything for broadening of the line width. So you have just a transition from one energy level to the other.
Right.
So that way you'll have like a sharp transition at a particular energy.
Right. So, okay. Yeah. Yeah, go on, Saurabh. Yeah, sorry.
Yes, sir. So you have a sharp absorption at one particular energy. So that way we can relate from like say Kramer's chronic to from absorption and find the imaginary part and then calculate the real part.
Yeah, that's excellent. So basically, what Saurabh was saying was that it kind of answers the entire question. So why do we have bands, right? If you have gases, you have individual elements, individual gases, and they have absorption energy levels which are discrete. We understand that because from the quantum particle in a box picture, we understand that there are these energy levels that come about. And now if you put many atoms together, they form bands. But when you talk of that happens in solids, you have the bands, but in gases, you will not have bands. You'll have individual energy levels, correct? And now if you want to talk about the absorption spectrum of this, what frequencies will be absorbed? Similar to what we have seen in the case of particle in a box. Let's say this is my energy level E1, E2, E3, and so on. So now when I have photon incident on this, I can have absorption in this way or this way and so on, right? So if I talk of this as delta E2, and this is my delta E1, depending on my the wavelength incident, I'll have absorption lines. Is that part clear? Let's say this is frequency, I'll call it delta nu, and this is my absorption, right? So now what we will see is for many of these wavelengths, there won't be any absorption, but only at certain transitions, you'll have this absorption. Something like this, right? This is maybe my delta E1, this is maybe delta E2, and so on. Okay. This is how your absorption should look like. And we understood, I think in the 7th or 8th week, we talked about the emission process. We said that emission is exactly the opposite of absorption, right? And so if you are somehow to excite these gases and let's say put electrons in this level, they'll immediately emit in this transition. So you'll have this particular line that is emitted. And similarly, if I put atoms in this state, I'll have emission in this line. So because of that, your absorption or emission spectrum is going to be this. Okay. So in our terminology, if you want to talk about the refractive index, Saurabh, you're saying something? Okay. So yeah. So so you'll have absorption or emission. In our terminology, we talked about refractive index as a complex quantity. Let's say refractive index n. We said it's a complex quantity, n1 plus I n2. Okay. My n2 is my imaginary part, right? Imaginary part. And this is positive for absorption and negative for emission. That's it. We called it also gain. When you have gain, you have emission. Okay. So if you ask about the refractive index of gases, we can easily understand the emission, absorption part of it is easy. Okay. What happens to the real part? So once you have absorption, the imaginary part is going to be these sharp peaks. Okay. And in fact, we can actually talk about the line widths of this from uncertainty principles. So we know from, we generally are aware of position and momentum uncertainty. Similarly, there is an energy and time uncertainty. So there is also an approximate relation, energy delta E times delta T should be equal to roughly H cross. Okay. H cross by 2, whatever, greater than or equal to. Okay. So now, if you take very sharp line, in this case, now I'm talking about energy line, right? If you have time, then the coherence properties of all this also will come into picture. So, sorry, Praneeth, who is here now? Praneeth? Hi, Praneeth. Praneeth? So there's a chat window. I'm sorry, I'm not seeing that. Just 1 second. Huh? Okay, no. Praneeth, if you want, you can actually type in chat or even speak, whatever you like. All right. So basically, you have the absorption process, which gives you the peaks. And then how will the real part be? That's a question, right? How do we determine the real part, Vinod? Pranit, you are not muted. In case you are not wanting to speak, I'll mute you, okay? Just please unmute yourself whenever you want. All right. Yeah. So, Vinod.
Hello.
Hello, yeah. What will happen to the real part of refractive index?
Sir, it will be stretched out.
It will be stretched out. How will it be stretched out?
Oh, sorry. I missed the previous part. Sorry.
No. The question was, let's say the absorption is okay, right? We understand how the absorption happens. There are these sharp lines that come about.
Yes, yes.
Okay, there's going to be some line width associated with that and all that. Now, what will happen to the imaginary part?
Imaginary part is like absorption. We'll see the real part.
Okay. So how will the... No, okay, let me step back a little bit. Why should there be finite line width here?
More damping, sir.
Damping? Why? Why should there be damping?
Means if we take the Lorentz oscillator equation,
yeah.
If in the denominator it will be some gamma term will be there.
Okay.
So which will reduce the full.
No, that's true. I mean, you have gamma term and the width of it is essentially the gamma term, right?
Yes.
That is okay. What I'm trying to get at is,
yeah.
For example, you have this essentially tells you that the lines are also slightly broader. Okay. Why should they be broad? If they are infinitesimally small, right? Then your delta T uncertainty in the time is going to be very, very large. Okay. And realistically speaking, if you have an atom, right, it starts emitting a particular wave, but then it decoheres. It doesn't maintain the coherence in itself. It's going to scatter with some other gas atom, and then finally the wave will be interrupted. There'll be phase jumps in the wave. So eventually, because of that, you're going to have some uncertainty in the frequency as well. Okay. You can think about it, like say from Fourier transform example as well. If you have a finite time window, then automatically the line will be broader, right? If you have an infinite time window, then it's going to be monochromatic, truly monochromatic. If you have a finite time window, it becomes slightly broader. All right.
Frequency and time are reversed.
Yeah, frequency and time are related by uncertainty relation effectively. Okay, or therefore your transform pairs. Okay, so yeah, so basically, if you look at this is a real imaginary part. If you look at the real part, we can calculate using what we call as Kramers-Kronig. Effectively, what will happen is if I draw in the same line, your real part is going to be something like this. Then again, there'll be peak, and then that's it. This way. Okay. Does it make sense? Praneeth or Supriya? Supriya joined just now, I guess. Hi, Supriya. You want to say something or have any questions? No? All right.
Sir, like
yeah.
For
Go
any,
ahead.
let's say, take any gas like sodium gas or a hydrogen gas, like what are the typical numbers of the refractive index? Let's say in vacuum, it will be 1.
Okay.
So for dielectrics, we'll talk about like 1.3, 1.4, or sometimes it will be 2 around. So what are the possible numbers for any gas?
Okay. So what are the typical values of refractive index of a gas, right? So, well, the main thing is when we saw the Lorentz model for refractive index, we saw that there will be this real part which goes like this, correct? Along with an absorption. And we said that there is this term. So eventually here it will be 1 plus chi. On this side, I think we said it is 1 plus chi plus omega p square by omega square. I think this is what we said. Okay. So now this omega p is a plasma frequency. And now this is related to the atomic density. N, right? N term. Now, if you have a solid, you're going to have a large atomic density. And hence, no, there'll be some additional number here. So if you look at this is what we called as, I believe, epsilon of 0. No, epsilon prime of 0, let's say. The real part, right? So there's going to be some number here. But if you go to, this is with large atomic density, like what happens in solids and liquids. But if you go to gases, the atomic density is going to be very small. Okay. So especially in the visible region, there is no refractive index. Okay. I mean, effectively, it will be close to 1 effectively in gases. Okay. Because remember, this chi also is the polarizability term. What will you talk of polarizability for a gas?
For a gas, yeah.
Right? Dipole moment per unit volume, but the volume is so large that overall chi is going to be very small. So effectively for gases, except where you have these absorption peaks, refractive index is 1. When you have an absorption peak, only in that very, very sharp delta E, right? Or delta frequency here, only in this region here, in this width, there's going to be a very sharp change in refractive index. In this, the red curve, in my red curve is slightly exaggerated actually. Okay. Because we can determine, right? We understood that Kramers-Kronig relations tell us that epsilon prime of omega is going to be proportional to epsilon double prime of omega. So there is an integral and so on, right?
Yes.
The Hilbert transform. So opposite also is true. So once you know the one, you can calculate the other. Yeah.
Okay. Yeah.
Yeah. All right. Thank you. Thank you, Vinod. There was some other question. Anyone wants to speak or say anything? You feel free to speak.
Sir.
Yeah.
If I'm not having a sharper peak of any solution, something.
Okay.
So if I make it into evaporated state, or if I make it pressure 0, so it will go into gaseous state.
Okay.
So will it give a sharper peak? It will happen.
Yeah,
if
yeah.
I create vacuum.
No. You mean to say that, let's say, somehow I have sodium in solid form and sodium in liquid in gaseous form, right? Let's say somehow. You're asking which will have a sharper peak in absorption?
Means gaseous form.
Absolutely. Absolutely, gaseous form will be sharper. Well, but it's not true for organic molecules. Organic molecules can have slight, larger width. See, think about it. No, like what happens in in organic chain, it's still, I think, it's sharper than what you see in solids. Okay. But bigger, the chain length becomes bigger, the quantum effects become weaker. So remember once somewhere, I think we talked about the particle in a box example and how the length of the size of the particle box will affect the absorption, right? Yeah. And by the way, there's also the selection rule idea that I think we talked about in the week 6, I think, where we said that all of these transitions are not possible, only some of them are possible, right? Delta n equal to 1 is possible, delta n equal to 2 is not possible, even is not possible, right? Yeah. So yeah, so gases will have sharper absorption line. That's true. So it's easier to detect in the gaseous state. But the problem is the larger signal, right? Signal to noise ratio. Yeah. Okay. Yeah. In fact, that's why I think some of these interesting experiments in quantum optics are actually done in gases. Things like rubidium gas are very popular, cesium gas.
The signal to noise ratio, how it is effective here? Going to be for organic.
No, what I'm meaning is, see, your signal is, if you have a solid, right, you're going to get a large signal because you have so many of these oscillators, right, close to each other. But if you have a gas, it's just one atom, right, in such a large volume. The amount of effective signal you get is going to be small, but it's going to be very sharp.
But still, sir, there can be some bonds. Like CO2 is a gas. There is a bond, and like this, there should be some bond.
Yeah, of course, there are going to be some bonds. If there are some bonds, they'll have some characteristic signatures here, right? But exactly same thing works even in FTIR. Okay. Right, where you see these absorption peaks, right, in FTIR. Chemists usually do that in FTIR. They see the sharp peaks because, sorry?
They do with solid or liquids. I don't know.
Oh, yeah, gases, of course, gases. Why do you think the FTIR is evacuated? You put it in you try to put it in the vacuum. If not, if you look at any FTIR spectrum, around 3.3 microns, you'll see a sharp, some variation you'll see, noise you'll see. That's because of the presence of water vapor in the air.
Okay.
So, yeah, you'll see that very easily. And I think water vapor is prominent at 3.3, I think, close to that. Yeah, you'll see that. Yes. Gases also will have a characteristic spectrum. Anyone? Any other question? Oh, one person joined and the person had signed out. Oh, 3 are watching actually online. Any questions from online audience? Yeah.
Sir, we are the 3.
I see. Okay. No, but then no, you're on Google Zoom, right? Not on YouTube. Actually, you're parallelly doing that.
Yes.
Okay. Okay. Now you closed it, I guess.
Okay. So, sir, can you just give a brief overview on what are the differences between a photonic band gap and an electronic band gap?
Okay, that's an interesting question. So the differences between photonic band gap and electronic band gap?
Yes.
Well, the ideas are similar. Why the band gap should occur and so on. The main thing is what does an electronic band gap do? What does it tell us? Let's say we have an electronic band gap. Let's say there is this valence band and there is this conduction band. Okay. Now, what does it tell us? So, it tells us that if you have a certain electron of, let's say, some energy here, electron of this energy, of somewhere in the middle of energy, right? Of energy in the band gap cannot propagate. Right? This is what it tells us. Agree with me?
Yes.
Why is it not allowed to propagate?
There are no states available. Forbidden gap.
What do you mean by that? See, a solid is simply a collection of atomic potentials, isn't it?
Yes.
Correct?
Yes.
Now, when we say that an electron cannot propagate on this, what does it mean? Hmm? So it means that if you have a certain periodic potential like this, you can simplify it in terms of this itself, right? The chronic penny model, we simplify it as a sequence of potential wells like this, correct?
Yes.
And now what we say is each potential well actually will cause some reflection and transmission, correct? So for certain combinations of incident lambda or incident, in this case, de Broglie wavelength, right? You can calculate the de Broglie wavelength of this electron, okay? So for certain combinations of these potentials, the electron is entirely reflected. Okay. So it cannot transmit in that region. That's what we mean. Okay. You understand what I'm saying?
Yes, sir. Yes.
So think of it like, let's say you have a lot of, let's say there is some rainwater and you have placed some bricks in a rainwater. Okay. Okay. Just to cross, there's a big puddle, maybe 10 meters long puddle. And then you have placed some bricks in that periodically. Okay. Now, if you try to walk across it, your speed and your wavelength has to be a certain amount. Only then you can actually cross. If you try to be somewhere which is, let's say half integral, integral multiple of, not integral multiple of lambda by 2, then you will step into the puddle somewhere.
Yes.
You will scatter. Okay. The beautiful thing is, even if you have, when we say we talk about in electronics, right? We talk about the drift velocity and so on, right? So we will basically, the beautiful thing is it behaves as if it's a single electron. See, whatever relations you draw, you derive, right? The force equal to charge times electric field. Right? You apply this much electric field, this will feel this much of force, it will move this much of distance and so on. All that is Newton's laws considering simple single charges. But even if you put a solid, the beautiful thing is, just because of this band picture, certain energies can transmit as if they behave with an effective mass. That's the only difference that you need to do, right? Instead of mobility being, whatever, it will become mu becomes E tau by m. Okay. As if it's instead of free space, you simply replace it with E tau by m star. That's all.
Okay.
As if it has a slightly different mass, it behaves. That's it. Nothing else. Even though you have this solid with so much of scattering potentials in 3 dimensions and so on, it still behaves very, very well. All right. Follow?
Yes.
So that is how an electronic band gap works, right? That's why we see that, okay, this particular energy cannot propagate in the solid. It's a band gap. But it's basically scattering. Electron will scatter from this potential well, from this potential well, from this potential well, and so on. Effectively, all of the electronic, wave function, the amplitude will be very high. Reflection will be high. Okay. No transmission. That means it cannot propagate. The same thing we see in the case of photonics. Let's say, for example, you talk of N1, N2, and so on, right? N1, N2, N1, N2, periodic potentials like this. Okay. When you have so many periodic potentials, just if you choose your wavelength, you will see that for certain combinations of periodicity and wavelength, you will see it will be reflected, mainly reflected. Okay. So lambda, if you have incident like this, for certain combinations, it will be fully reflected. And this will be transmitted. Correct?
Yeah.
This is a band gap. So ideally speaking, at least in my view, the band gaps are similar. There's no difference. Photonic band gap or optical band gap, they're all similar. It's just that if you have an electron, it has a dispersion relation of h cross square k square by 2m. This is its dispersion relation. Whereas for a photon, what is the dispersion relation? Equal to
Plus lambda equal to h by p.
Lambda equal to, I mean, yeah, we have various forms of doing that, no?
Yes.
So E equal to H nu.
H.
Okay.
Yeah.
Or, you know,
P
what
by
is
C.
E?
E equal to P by C we can write.
E equal to P by C. What is that? P by C. Acha. How? It will be PC,
PC,
not P by C.
Yeah, sorry, yeah.
Not P by C. Okay. Or we can write it as, I mean, you can simplify this, right? If you want to call this, I can, no, we have various forms, exactly same thing. You can write as H cross omega equal to HC by lambda, right?
Yeah.
And that is equal to H cross by 2 pi into 2 pi C by lambda, right? So if I take out omega, what will be? This will be, so if I take this will be my, if I take out H cross, basically this side will cancel out. So omega equal to 2 pi by lambda is what? K. Omega equal to CK.
Okay.
So we said this is a dispersion relation, right? For yeah. Okay. For light line, light line we talked about this, and then we said that if you draw the dispersion, it will be like this: K versus omega. Right? The slope is C, or the speed of the wave in that particular medium, and so on. Okay. So yeah, I mean, there's no difference between optical or electronic band gap. They have lots of analogies. Only thing different is what? What's the key difference between them? What's the key difference? Anyone? Length scale. Okay. If you talk of electronic band gap, what's the length scale involved?
Electron volt.
Length scale, my friend. Angstroms. Atomic lengths. Atomic bond lengths. Right? Lambda, I mean, or you can call it, the de Broglie wavelength of electron. Instead of this one, I can even call it de Broglie wavelength. Lambda E, I'll call it. Okay. All right.
Yes.
So you need to have atomic bond lengths. Only then you will see the band gap effects. Okay. In the case of optical band gap, lambda in the order of the periodicity in the order of A, right? Sorry, periodicity in order of lambda. Okay. In this case, also same thing. So atomic band gaps, atomic bond length, this will be A will be in this case, maybe 100 to hundreds of nanometers to generally in the range of hundreds of nanometers for a visible range. Correct?
Yes.
If you talk of IR, it will be larger. Okay. So now that's the key difference. So that also tells you why, if you take an electronic material, let's say for example silicon, and shine photons, why are you not considering the band gap? See? Why? I mean, indirectly. Why? I mean, you think about it, no? This is basically the distance. Why silicon behaves like an effective medium? Correct? Why silicon behaves like an effective medium? For example, if you take this, because the wavelength is basically, for example, if you take visible 500 nanometers, is much, much greater than the atomic periodicity, right? So that's why it effectively behaves like an effective medium, and you ascribe a refractive index and so on for that. You treat it macroscopically. All right. Whereas in the case of electronics, we have to worry about that as well, because the de Broglie wavelength is very, very small. Okay. So effectively the same phenomenon, multiple length scales.
Okay.
I don't see them as quite different. All right.
Yes.
Yes.
Thank
Anyone else? Yeah.
Sir, can you hear me?
Yes, I can hear you, Saurabh.
Yeah, I was trying to get my audio back. Sir,
All
actually, I just wanted to ask, like, when we talk about lasers and all, you also saw that there is something called as plasmonic lasers made out of plasmonic material.
Right.
We remember in week 3 or 4. I just wanted to ask if, how is it possible to have like lasers made out of a material which is glossy? The same metals or something. Or what are the characteristics or differences between dielectric and plasmonic lasers?
Okay. So effectively, okay, the question is, we talked about lasers and we understand that lasers are, we have certain conditions for lasers, right? We want population inversion, we want a cavity and so on. But we understood in the week 2 and 3, I think we understood about the metallic properties, optical properties. And we said metals are lossy. If metals are lossy, how can you have a plasmonic laser? Because laser wants gain, no, not loss, right? How can you have a gain? Okay. Plasmonic laser seems to be a non-starter. Well, it turns out that, in all the demonstrations of plasmonic laser, we add a gain medium. We balance out the gain, loss, balance out the loss with gain. So we have to have certain amount of gain. Only then you can actually have plasmonic lasing. In that, famous paper of, 2009 or so, they had incorporated dye. A dye effectively acts like a gain medium. You pump the dye, you create a population inversion, and then the cavity is small enough, so you excite a plasmon in that, and then plasmon gets amplified. Okay, so plasmonic lasers can work only when you have some gain. It's difficult to actually get plasmonic lasers without gain. Okay, and there are different types of lasers here. Some people also demonstrated what we can call as lattice, based. Basically, you have a periodic structure. And if you have a periodic structure, you will have, if you put some gain material on it, for example, coat it with some dye solution, then a lot of gain is there and small amount of loss at the plasmonic structure. But then they support certain modes which are very, very sharp. And because of that, in those modes, you have emission of radiation. Okay. So yeah, you can that's a key difference essentially. You're right that you cannot have losses and lasing. We'll have to somehow balance out the loss with some gain. And the way to create gain is by pumping with some energy. The same thing happens even in regular lasers. If you build a cavity, there's going to be a certain amount of loss, right? And the losses have to be overcome by, when actually gain is higher than the losses, only then lasing occurs. And that is the reason why you need population inversion and you need to pump it at a certain point. And we call that as threshold. Only when you pump a laser above a threshold, then you see lasing, not below a threshold. Below a threshold, it's simply, spontaneous emission, amplified spontaneous emission. That's it. Okay. So you have to pump the laser above a certain threshold to actually start seeing gain or lasing.
Yes, sir.
Yeah, answer. Okay.
So you said amplified spontaneous emission, and like, what are the signatures? What signatures do we look for when we look at nanoscale lasers?
Well, okay. Yeah, that's an important point, right? I said, yeah, broadly. What do you mean by amplified spontaneous emission? First of all, that's a question. I use the term, but what does it mean? So you can think about it like this. When I think at some point we talked about even the gain spectrum and so on for the semiconductor. Let's take the example of semiconductor, H nu, and this is gain, let's say. Okay. We said if you pump it hard, then over a certain range, you have basically gain. And this is basically EG. And this is, can somebody help me? FP minus Fn. The separation in the quasi-Fermi levels. Only at certain range of wavelengths, you can have gain. Okay. Now, if you put a cavity, in principle, you can have emission at any of these wavelengths. So you will get a broad spectrum. Okay. And the spontaneous emission can occur at any point. Okay. And it gets amplified because within the cavity, it gets built up. That's why we call it amplified spontaneous emission. that will happen initially, but once you cross a threshold, what happens is only a certain wavelength will get selected by the cavity. Every other wavelength will be rejected. Okay.
Yes.
Certain lambda within the gain bandwidth is selected by the cavity. Okay. Only that will happen. None of the other wavelengths will lace. So that gets again fed back again, it just gets repeatedly, enhanced. And then finally you get very, very sharp, very, very high intensity beam. Laser amplification, right? Light amplification happens in lasers. So this is a process of amplification. Whereas some wavelengths which are away from this will not get amplified. So when you start seeing a laser, I think I showed in one of my slides, where initially the spectrum will look like this broad, and slowly a peak will start coming, and the peak will become sharper and sharper. Okay. Eventually you get almost like a single monochromatic wave. Single peak emerges. Okay. So this is one of the significant, this is one of the characteristics of a laser. Okay. So in one of those slides, I think I even showed you, we didn't spend time on that, but as you increase the input power or pump fluence, initially you'll see that the FWHM is high and then it drops. Okay. There's a broad emission, then slowly a peak starts emerging, and then finally that shows a characteristic dip. So that is called as lasing. Okay, when the dip happens. That is, very the older way of looking at it. It turns out the scientists have seen that if you have a very sharp Q factor in your cavity, it will always have very sharp emission there. So narrow line width is not necessarily signature of lasing. You can even know that. For example, if you look at a white light and somehow filter out every other color except green, then the light will look green. But is it really laser? No. The color does not capture the color is not sufficient, right? To claim lasing. Because you simply block out every other color, only one color will come. So it only says that it's a very sharp filter, not a laser. So one of the true effects that people accept is actually the second order correlation function, G2. We talked about G2, I think in week 9 or 10 somewhere. And we said that if the G2 of 0 is equal to 1, then it's a signature of a perfect coherent beam, light. So if you take a laser, we have to show that G2 of 0 equal to 1. Generally, it will be slightly higher than 1, but it's still okay. It's at least sharp. Okay. Yeah. All right.
So, you said we need gain material to overcome the losses of metal losses.
Mm-hmm. Mm-hmm.
So, let's say, in a way, say surface plasmons are also, since they propagate on a metal and are lossy, they propagate for a certain distance and they die out.
Right.
So, has there been any progress in using this gain material to enhance the propagation distances?
Oh, definitely. Yeah. We talked about surface plasmons. We said that, okay, there's going to be some propagation length, and after which it will get decayed and so on. And if you can increase the propagation length of a surface plasmon by actually coating some gain solution on top. Yeah, people have shown that experimentally. So if you have a gain medium at the wavelength of propagation, SPP wavelength, then you will see that if you don't have gain, it will propagate a shorter distance. And when you introduce gain, it actually propagates longer distance. You see that, yeah. That's true. Did I answer?
Yes.
Yeah, okay. Good. So,
So one more last question regarding the same.
No issues, yeah, please.
We think like metals are lossy, and because of that, it's kind of difficult to integrate them. Mm-hmm. But when it comes to electrically driven, if you want to achieve electrically driven lasers and all for on-chip purposes, nanoscale, it would be very difficult to not have metals in the structure, because they will form the contact and stuff.
Right.
So how do we reconcile that fact that, how do we get over those losses? And
well, I mean, okay, it's a trade-off. You cannot avoid using metals, because if you don't have metals, you can't make contacts, you can't electrically pump a laser. So that is true. Now the question is, you cannot make it very thick that nothing comes out. You have to make it thin enough so that you get some transmission out of it. But then it should be a good quality metal. So it's a lot of complex design process that's involved in actually generating actual, coupling out the laser.
Yeah.
Okay. But one beautiful thing is, if you go back and think about the way we described the laser, right? We talked of these two mirrors, M1 and M2. And then these are just 1% reflection, let's say. Okay. The transmission is 1%, sorry. Here also transmission is 1%. So if you just have single mirrors cascaded, you will see that very small amount of light will get through. Okay. 0.01% should get through ideally. But because of the presence of cavity, so much of energy builds up here. Okay. Effectively, if you take an intensity of 1 watt here, 1 watt will come out at the resonant wavelength. Even though you have the absorption and reflection and so on, whatever, The reason is intensity here, you can think of it will be like 100 watts. So then 1 watt of it will come out. Even if you take a passive structure, you'll see that the transmission is very high at the resonant wavelengths. And that's what I think you have shown one picture from Vardhan, I believe.
Yes, sir.
If you don't have the resonance effects, that is, if length is not equal to n lambda or m lambda, then you don't have resonance, and very small absorption, very small transmission happens through this. So even though your cavity is, the walls of the mirrors are actually very reflective, it's still working as a laser. That 1% transmission is necessary. If you don't have that also, then you can't have any outcoupling of laser.
Yes.
Okay. So coming back to your question, the question was, I'm sorry, no, you were asking about electrical conduction, right? Even if you have losses, it's going to have some impact, but at lasing, I think it's still workable. Only thing is we have to control the non-radiative decay. That becomes a challenge, but people have figured out some ways to do that.
Sir, anyway, transparent conducting oxides can help.
Oh yeah, of course, transparent conducting oxides can help, because you have, but only thing is their conductivity is still low. You can't probably operate them very, very high speeds.
Okay.
If you're okay with low speed, for example, transparent conducting oxides are used in solar cells. You can't put a metal contact on top. If you put a metal contact, all the light will reflect. So they put transparent conducting oxides, but then they are looking for milliseconds response, or light. It's you don't need to drive it fast. So it's okay. It works. But the moment, let's say, if you want to modulate a LED, if you put a transparent conducting oxide contact, then the modulation speed will suffer. You can't operate at gigahertz if you want to. Okay.
Yeah.
So it's a combination of resistance and temporal response. Yeah.
Oh.
Okay. Any other question? Well, yeah. Anyway, so I think we have covered some very interesting topics, but I believe people have. I think it has become very heavy for the students, especially if they're undergraduates. I'm sure it can be pretty heavy. So let's see. Yeah. Let me know whatever, your, if you're interested in something specific, we can answer. Please talk to us on the forums and so on. We'll interact again and again. All right. So I think it looks like, finally there are no other questions. Can we stop this, Balaji? Balaji? Or I'll call him and tell him that, we can stop, I guess.
Yes.
Yeah, just a minute. Let me see. Balaji, can we sign out?
Yeah.
Yes, sir.
Because I think there are no more questions and,
Okay, sir. We can close it.
Yeah, we can close it. Yeah. Yes, Balaji, I just want to speak to you. After you close, I'll continue this. Just hold on the call. No?
Yes, sir. Yes, sir.
I'll just close it and we'll talk. Yeah.
Oh, okay.